All right, so today what we're going to do, probably through most of the class, if not all of it, is work on the sample midterm. Okay, so let me get it open. Go to Moodle and download it. Now, of course, this is chapters 3, 5, 6, and 7 only. 8, which we just finished yesterday, is not on the midterm. It'll be on the final, of course. So for now, we'll put that aside and we will look at the sample midterm. And if you're able to do the sample midterm, the test itself is very, very similar to the sample midterm because it covers pretty much everything we did. You'll see when you get to the test that there's no intent to be tricky or anything like that. It's just exactly the same material. So like I said, if you can do this, you can do the test with no problems at all. And you don't forget, you'll also still have the opportunity to continue to ask questions if you need to. Like, for example, if there's something unclear about the questions, or if you're not sure what it means or something along those lines, that's fine. We can always go over it. All right, so there's a list here. And like I said, don't worry about Bayes' theorem. That won't be there. This is the only thing that really doesn't belong here now. But other than that, everything else that you see listed here is fair game. So let me just quickly save this. And all right, let's see where are we? There we go.
For one of them, when she initially asked the sales associate about buying a Birkin, the associate said, "Ensure that you're deserving of a bag before they consider selling one to you." It's a pretty arrogant thing to tell your customers. So what do you have to do to deserve a bag? You have to go to that store over a long period of time and spend tens of dollars on their other products, whether you want them.
All right, let's do it. All right, now in the beginning, as I mentioned, we do have these short fill-in questions. And so we'll just go through them one at a time. Now, in each of these cases, typically the answer will only require 1 or 2 sentences. In some cases, maybe even 1 or 2 words will be enough. So you can resist the temptation to write a whole essay, but as long as the correct answer is there, you're fine. So what are the 3 axioms of probability? All right, well, number 1 was that the probability of any event is non-negative. Now, what you can do here, oh, hold on one second. I have to plug in my tablet here. In some cases, you have an option or choice between writing it out in words or in just, symbols. And in those cases, you can do either one. Like here, for example, you could write what I've just done here, but what you could also do is simply write probability of AI, where AI is some event, or it doesn't even need an I, sorry. In this case, we just wrote it as PA. The probability of any event A is simply restricted to being positive or 0. 0 is allowed, not negative. We cannot have a negative probability. Number 2, the probability of the entire sample space is 1. And then for that one, what you could have done alternatively, or you could do them both if you want, is write the probability of S equals 1. Okay, and that's all you need. The third one's a little bit trickier. And basically, it says that for any collection of disjoint, which is another word for mutually exclusive events, we have the following result. So basically what's happening is you're taking the probability of a union, and this particular union, we will have potentially many, many different events. So we'll have unions of A1 with A2 with A3, all the way out to AN, whatever that is. And this could be any number of events. And that simply equals the sums of the individual probabilities. So basically what you're seeing here is the general case of the simplified addition rule. Okay, in other words, this is the simplified addition rule, but applied to n events rather than just two. So this is the justification for that. Because they don't overlap, the probability of their union is nothing but the sum of the individual probabilities. So that is one of the three axioms on which the entire set of probability theory is based. All the rest of the results are taken directly from here. All right. And by the way, in the test, it might only ask you for one or two of these axioms. It may not necessarily ask for all three. So then you just pick the one you want. It doesn't really matter. All right. Now, what conditions must be met for two events to be independent? All right. Well, there's two of them. Assuming we're dealing with sets A and B, or events A and B. And that's it. All right. Essentially, what this is saying is that knowing that B is true does not affect the probability of A, and knowing that A is true does not affect the probability of B. That's what it means to be independent. Right? Now, you can think of some examples. We talked about one where we were talking about the stock market and the weather. Clearly, the two have nothing to do with each other. So knowing that it's raining, for example, does not affect the probability of the Dow Jones going up and vice versa. Now, for the correlation coefficient, which we saw in chapter 3 towards the end, the correlation coefficient assumes a value between -1 and +1. Another thing you could do is use symbols. Remember, we used this symbol for the correlation coefficient of a population. This would also do the job. If you want to write out symbols like that, you can go ahead, but it means the same thing. Okay, so that's the range of possibilities. And of course, you recall that that's one of its big advantages over the covariance. The fact that we have an upper and a lower limit makes it much easier to interpret what our results are telling us. All right, so far so good. Let's see. If a sample is negatively skewed, and let me just quickly draw you a little sketch of that. No, that's no good. Let's do it like this. Okay, so when we did this, we had histograms and they were bars, but still the basic shape is this. You've got a large number of values down over here, and then we have this extremely long left tail. This is the case where the mean is the smallest of the three measures and the mode is the largest. Okay, so when we have the situation, the sample is said to be negatively skewed and we have a result that looks like that. All right. Now, and the other two cases were, of course, in the same chapter. You can go back and look them up. When the actual test might ask you what's going on when the sample is positively skewed, for example, or symmetrical. And so when it is positively skewed, the mean is the largest of the three. And when the sample is symmetrical, all three of them are equal to each other. All right, well, here's an easy one. An event is a sample, a subset, sorry, of the sample space. That's all it is. Literally, it's just a subset. Any subset qualifies as an event. All right, here we go. Now, what about complements? Now, as is so often the case, there's a couple of different ways you could actually express this. And so you can write it in one of two ways. You can either show that A union B is the entire sample space, or A intersect B is the empty set. The other alternative would be to show this, because it means the same thing. Now, in some of the problems that we worked on, we may not have known the actual values of A and B, but we were given their probabilities. So either one of these will do the job. You don't need both, but either the first set of statements or the second set of statements will be enough to prove that these two events are complements. All right. If A and B are mutually exclusive, what is the probability that both of them will occur? Well, by definition, that would be 0. Okay, because this is defined as an impossible event. If A and B are mutually exclusive, it would be like, imagine if A represents picking a red card from a deck and B represents picking a black card. The card can't be both. Therefore, the probability of A and B is just 0. All right. Simplified multiplication rule. Remember, that's this one. Whoops, sorry, wait, sorry. I wrote this incorrectly. Sorry about that. Hold on one second. I just realized I'm typing the wrong thing. Hold on one second. And so we can only do this. This rule can be used when A and B are independent. Independent is required for us to use the simplified version. Okay. Now, an experiment consists of choosing a single card from a deck. A is the event that the card is red. What would be the complement? Well, you could define event B is the event that the card is black. B is the complement of A. Why is that? I'll put in the explanation here. This is because all the cards are either red or black, and no card can be both. So that's the logic behind this. In other words, all the cards are one or the other, but no card can be both. So this is what complements actually are. Just like the even and the odd numbers, and the white and the black pieces on a chessboard, that type of thing. When is the simplified addition rule used? Now remember, up here, we're asked about the simplified multiplication rule. Now it's the simplified addition rule. This is very different. That's this case. And we do this when, or we're allowed to do this is used when A and B are mutually exclusive. Okay, so with the multiplication rule, the simplified version requires A and B to be independent. Here, they're required to be mutually exclusive, meaning they have no elements in common. Okay, so be careful, don't get them confused with each other. All right. A discrete random variable. So the word discrete in this context simply means there's a finite number of possibilities. So a discrete random variable assigns numerical values to the outcomes of an experiment where the number of possible outcomes is finite. The key word to the whole thing right here is finite. That's by far the most important word in the sentence, finite. Okay, now for question 12, we're going to ask about the continuous random variable. So for that, I only need to change one word. And since I'm using a word processor, I'm going to take advantage of it. All I need to change is this last, oh, actually, I forgot. I need to change this to infinite. That's the only difference, finite versus infinite. All right. Now, which probability distribution is based on a series of independent trials? That would be the binomial distribution. Remember, that's how it's defined. We have a series of independent trials of which each one can only take one of two values, success or failure, and the probability of success is a constant. So that would be this one. As opposed to the Poisson, where we're looking at time passing. Now, this question is a little bit tricky. Which probability distribution has the same expected value and variance? So what exactly are we talking about here? Well, if you think of the shortcut formulas for your moments, remember we have the expected value, we have the variance, and the standard deviation. And you recall there were shortcut formulas. The one that we want to think about is Poisson. Expected value is equal to lambda, variance is equal to lambda, and the standard deviation is radical lambda. So because these are equal to each other, that must be the correct answer, the Poisson distribution. It's the only one where this is true. Now, for the next one, the two values that uniquely characterize the normal distribution would be the mean and the standard deviation. Which is sigma. That's it. That's all you need to know. Remember, we showed that when you draw graphs of the normal distribution, the mean represents the location and the standard deviation represents the shape. Okay, great. What is the variance of the standard normal distribution? Well, remember with the standard normal, the mean or expected value is 0, right? The standard deviation is 1, which means that this variance must also be 1. All right, so we mentioned that in the slides that the thing that separates the standard normal from the rest of the normal distributions is the fact that the mean is 0 and the standard deviation is 1. But what that implies is that the variance must be 1 because you're just squaring the standard deviation. Okay. What probability distribution can be approximated within, well, we spent a lot of time with this one. Yes, the binomial distribution can be approximated with the normal distribution. the variance of a binomial random variable. Now remember, these are the moments. This is one of those shortcut formulas. So you might want to have in front of you a list of these shortcut formulas when you're taking the test for binomial and Poisson. We have these special quicker formulas for calculating the moments. And this was the moment for the binomial random variable. All right. What does lambda represent in the Poisson distribution? Now, lambda, if you've forgotten, is this character. In fact, let me sneak that in here right now. I should have it right here. That's lambda. So lambda represents the average number of events that occur during a given time interval. And that has to be given to you in the problem. You can't be asked to calculate that because you have to be told what it is. All right, and then finally, what formula is used to transform a normal random variable into a standard normal random variable? So this is the formula we've seen about 100 times. Z equals X minus mu over sigma. All right, so remember Z represents the standard normal, X is normal. Beautiful. All right. So now we're ready for the problems. Okay. Oh, by the way, I'll be posting this, of course, when we're done. So if you missed something, you can go double check and look at it. So we've got a sample. This is going back to chapter 3, and we're going to calculate all the following measures. And let's see. We start with the mean. So what do we need to do? So with this one, we don't need to do any actual sorting. Let me just split the screen up for a second here. There we go. Yeah, we want to always be able to see the elements. That would be kind of helpful. All right, let's do the mean. And by the way, don't forget, you should right away pay very close attention to whether this is a sample or a population. All right, so we'll start here with the sample mean. So here we're simply adding in the numerator all of these terms. And so when you add them up, you get 12 over 6, which is 2. Now for the median, what we need to do is take the sorted values, and those are -1, 0, 1, 3, 4, and 5. So we note here that since there are an even number of values, we average out the 2 in the middle, which is the 1 and the 3. So we also get a 2 for the median. Okay, so where did that come from? Again, we're sorting out these two. Sorting out. We've already sorted. We're averaging out the 2 in the middle. If we had an odd number of values, we would have just gone directly to the center. All right. C is the mode. Since no values, you can tell by looking at the sorted values, no values are repeated. There is no mode. Okay. So for something like that, it's probably easier to simply look at the sorted values. But with such a small sample, I mean, you can tell there's nothing that's being repeated. But I think for something like this, it's your best bet is to sort them out. Now D is, I believe, let's see, the third quartile. All right. So once again, we'll take the sorted values. And the quartiles depend also on whether there's an even or odd number of values. So we're looking for the third quartile, which is often written as Q3. So most likely the easiest thing to do, we already know what the median is. This is also the second quartile, Q2. Now, the reason why that matters is because what we're going to do is split, hold on one second. Split the data in half. So that we actually have two sub-samples, or two samples, I suppose you could say, or maybe we could call those subsamples. But anyway, we're breaking this up into two groups. The lower half and the upper half. And so the way this works, yeah, it would be nice if it all fit on the same page. Let me just move this down a little. So the first quartile, or the third quartile, which is what we're looking for, is the median of the upper half, which is 4. It's easy because you can go right to the 4. It's right smack in the middle. Okay, so that's it. So we split it up and we discover that in the upper half of the data, the median of the upper half is 4. And it's easy this time because we only have 3 values. So it's right there. All right, now E is the range. And that's equal to the, yeah, I gotta get a new computer. This thing is really, I'm gonna throw it out the window. The range equals the maximum value minus the minimum value. So, and again, it's probably easiest to take a look at your sorted data to do this. And therefore, you just have 5 minus minus 1, which is just 6. It's very straightforward. Now, for F, the interquartile range is the difference between Q3 and Q1. But we don't know Q1, do we? No. But it's easy because here's what we'll do. We'll go back and revisit what we did up here. And we'll note that while Q3 is the median of the upper half of the data, Q1 is the median of the lower half. And of course, that would be 0. All right, so this is Q1, and this is Q3. So that means that the interquartile range, which is Q3 minus Q1, four minus 0, which is 4. Okay, and then we're done. All right, now, G is the variance. Now, this is a sample variance. So we don't actually need to sort the data to do this. And so here's what we're going to do. Let's go back and get the data. Now, remember, the sample variance looks like this. Now, X bar, we've already calculated as 2. So we don't have to worry about that again. So what we do have to worry about is entering everything correctly into this formula. It's a very messy formula. So let's go through it one at a time. And if you notice what I'm doing here, I'm going through these numbers one at a time. And for each one, I'm subtracting the mean of 2. Okay, what just happened? Okay. It decided to move itself up there. Isn't that nice? I love it when that happens. Again, now I've completely lost everything I was doing. All right, let's try that again. Let's see if it'll allow me to do that. Five minus 2 squared. I was trying to indicate that this is coming from here. And then we go up to this one. And then the next one. And then finally this one. Now, here's where we also have to watch it. In this case, n is 6. There's 6 observations. So according to the formula, what we're going to do here is divide not by 6, but by 5. All right. So now that we've done that part correctly, what we have to do is interpret it, or evaluate it, I should say. And so that means, for example, here we'll have minus 3 squared. It's minus 2 squared plus 3 squared plus 1 squared plus minus 1 squared plus 2 squared. And then we go ahead and evaluate those numbers, which, let's see. There we go. I can just about squeeze that in there. All right, so we've got 28 over 5, which is 5.6. And that's the sample variance. So you can see it's a multiple step process, and it's really all about being careful. It's so easy to make mistakes with something like this. So just be careful. And by the way, I encourage you to show your work. I don't think I mentioned this earlier, but or maybe I did. If you show the steps and you make a silly mistake somewhere along the way, I can give you most of the credits, sometimes all of them, because I can see that you did everything right, except maybe you forgot to square one of the terms. If you just write the wrong answer, there's not much I can do about it. You just lose all the points. So the more you show what you've done, the easier it is for me to give you partial credits. And also, I think it helps you organize it yourself. You know, I know it sounds like a lot of work, and you're like, I don't want to write all these steps. But if you do, it makes it much easier to get partial credits. Think of it as an insurance policy. You know, you don't want to pay for that insurance in your car, but you know you have to. What else? Because otherwise you're bound to get into an accident. All right. So let's see. Was that it for this one? Oh, no, we're not done. We still have the coefficient of variation. Okay. All right. So the coefficient of variation . The coefficient of variation is nothing but the standard deviation over the mean. Whether it is a population or a sample, it's still the same logic. So here what we'll do is we'll put in here S over X bar, 5.6. Oh, you know what I forgot to do? I forgot to put in the standard deviation. Sorry about that. Part H, I completely missed it. There, yes, I sure did. Okay. Hold on. Part H. Let me just sneak that in here. Yeah, I mean, usually when you calculate the variance, the next step is to calculate the standard deviation. So standard deviation, the standard deviation is always the square root of the variance. Okay, so here, that means that S squared, S is the square root of S squared, or the square root of 5.6, which is approximately 2.366. Okay, now that matters a great deal because we need that for our coefficient of variation. Without that, we can't do our coefficient of variation. So therefore, we'll have 2.366 over 2 times 100, which works out to be about, let's say 118.3, which is a percentage. So in other words, the standard deviation is about 1.2 times as large as the mean. All right, now for this next one, they're asking us, they're giving us this data. And if you notice right away, you've got a set of daily returns for a stock. These returns took place over 50 days. And so we can think of that as a sample of 50 days from as outside of or taken from the lifetime of these stocks. And so if you notice, this is the key detail. Many of the returns took place more than once. So in other words, you have 50 trading days, but you have a lot of repeated values. And when that happens, it's often easier to use a weighted average than just use X bar. And that's what's happening here. Plus, in this case, we don't actually have the original data. All we have is the summary of it. So we really have to use a weighted average anyway, since we don't have the original information. So if you recall, the formula for weighted average looks like this, for sample at least. You've got X bar equals, now in the numerator, you have the sum of the weights times the X's. And down here, you just have the sum of the weights. Now, if you look at this chart, which is which, these are the weights. The frequencies in this case are the weights. That means these are the X's. Because that's what we're really analyzing, the average rate of return. We're not interested in the average frequency. We're interested in the average rate of return. So that's how you know that these are the X's and the W's are the frequencies, because the frequencies tell us how often this happened. So now we just plug everything in. So let's see, let me split the old screen here so I can see what I'm doing. Oh. There we go. All right. So what we're going to do is this. All right, and so that, I just wanted you to see, that's what the formula actually tells us to do. Whoa, whoa, okay. So now I'm just gonna actually start throwing in those numbers. And so we'll have 10 times, oh, by the way, whenever there's percentages involved, I always recommend that you convert these into decimals. And then at the end, you can convert them back if you want to. I just find that it's much easier to avoid mistakes this way. So if you notice in each case, I'm starting with the weight and then multiplying by the corresponding return. In the denominator, it's just a simple matter of adding up the weights, which we already know is equal to 50, by the way. All right, and so now, let's see where this leads us. All right. So that should leave us with all right, and let's see when we add those up. Oh, I think I goofed somewhere. No, maybe not. Let me just double check this. Let me get. I'm just going to double check this really quickly. No, it's good. Okay, great. The numerator is negative 0.12. The denominator is 50. Now, when you divide that out, you're getting negative 0.0024, but in percentage terms, this is negative 0.24%. So in other words, on an average trading day during this period, we lost about 0.25% on our portfolio. Oh, I just realized somebody, yes. Oh, you mean for the first? No, the first one is supposed to be negative 0.2 because you're multiplying 10 times 0.02. This one, you mean? Right here, this one should be negative 0.2. This is negative 0.12, 0, 0.08, and 0.12. Yeah, that's right. All right, we're good. Excellent. Okay, you see how easy it is to mess it up? Very, very easy. You have to be super careful with this stuff. And of course, that's why we wanted to write down all the steps, because if you made a mistake, you could get a lot of partial credits. All right, we don't want anybody to lose all the points. So the average daily return, I guess we'll put it right here, is about a loss of 0.25%. All right, so the key to the whole thing was just recognizing that it is in fact a weighted average problem, but you should have no difficulty with that because like I said, you're given a table with frequencies instead of the original data. So that's a hint that this is meant to be a weighted average. All right, now this next one is going to be the most time consuming one because we have to calculate the covariance and the correlation. Wow, that's a lot of work. This will be the most time consuming one, that's for sure. So first things first, whenever you have something like this, your first step is to always calculate the mean of each sample. And also, if you notice, it says right here that these are samples. So the covariance looks like this. And then the correlation coefficient asks us to take this covariance and divide by the 2 standard deviations, which means we have to calculate all 3 of these, the covariance and the 2 standard deviations, just to come up with a single correlation coefficient. Okay, so anyway, before we even do that, we need the sample means. Okay, so the very first step is to calculate the sample means. So we have -3 plus 0 plus 4, 2 plus 7, all divided by 5, which is equal to 10 over 5, 2. So the mean of sample X is 2. For Y, one plus 5 plus 6 plus 7 plus 1. That adds up to 20 over 5, which is 4, of course. Now, this covariance formula is pretty tricky. Let's see. I'd like to be able to show this all in one shot. Let me see what I can do here. So SXY, now here's what we have to do, and this is going to, I probably have to write it over 2 lines. You have to go through all the X's one at a time. For each X, you're subtracting X bar. And then the same Y. For the same Y, we subtract Y bars. In other words, what we've done here is this is X1 minus X bar, Y1 minus Y bar. Now we go on to 2. X2 is 0. Y2 is 5. And in each case, again, once again, we're subtracting the mean. Oops. And then we have to do the same thing for all 5 of them. Okay, and when we're done, we're going to divide by n minus 1. So let's see, the third one is 4 minus 2, 6 minus 4, and then there's still 2 more. For the 4s, 2 minus 2, 7 minus 4. And then we have to go to the 5th row, 7 minus 2, 1 minus 4. Oops, X5. and then y5 minus y bar. Finally, after all that, we're divided by 5 minus 1. Now, in this case, n is 5. Both samples have size 5. They have to have the same number of elements. Otherwise, the formula doesn't work. Okay, so we're dividing by actually by 4. Now we get to interpret all this. Ooh, this is going to take a while, like I said. Don't worry, you'll be at home doing this. I'm trying to find exactly the right spot where I can fit in everything. All right, so like for example, here we'll have minus 5 times minus 3. Then next we'll have minus 2 times 1. 2 times 2, 0 times 3. 5 negative 3. 15 minus 2 plus 4 plus 0 minus 15 all over 4. Well, this one turned out to be 2/4, which is a half. All right, and that's it. Finally, after all that work, the covariance is a half. Now, of course, that tells us that there's a positive relationship between x and y, but it doesn't tell us how strong that relationship is. For that, we need the correlation coefficient. Now, unfortunately, that also means we need to calculate not just one, but 2 standard deviations to get to this point. Luckily, I guess we can use the practice though. So what I'm going to do is copy the data down here again so we can see it as we go along. So now we're ready for the 2 standard deviations, which we already know how to do. It's more of a nuisance than difficult, but it is difficult. It is a nuisance. Here we go. All right, you know what I'm going to do here? I know from experience that unfortunately, the great thing about this tablet is that I can write whatever I want in here. The unfortunate thing is that it takes up a lot of space. And so I think what we're going to have to do here is I'll finish this up and then I'll have to start a new document to cover the rest of these questions because otherwise it won't save properly. So let's see, I think I can just about finish this part without having a problem. So I may have to split this up into 2 documents just because I'm worried about the space restrictions. I've run into this before. If you go too far and have too much information in here, it becomes an unbelievable hassle to get it saved. So we'll just wrap up this part. It's almost break time anyway. And when we get back, so don't be surprised when you see 2 halves of the solutions. So if you recall, x bar was 2 and y bar was 4. So in other words, what I need to do now is calculate. We'll start with the variance of x. And just quick reminder, That's the formula for the sample variance. Okay, now here we have a subscript because we have two different samples. We have to keep them separate from each other. So let's run through them. Now, so here I'm just focusing on the x's only. Go through them one at a time, and in each case I'm subtracting x bar, and then here I have to square them. And again, in the denominator, divide by not n, but n minus 1. All right, and then we'll get 25 plus 4 plus 4 plus 0 plus 25. 58 fourths, it looks like. Let's see. 58 over 4 is equal to 14 and a half. Now, of course, that's the variance. It's not really what we want. It's the standard deviation that we're after. And so that's approximately 3.808. Excellent. Now we have to do the same thing for y. So I'll split the screen. And again, once again, reminder, y bar is 4. So we'll start with the sample variance for y. So I'll go through them one at a time. Each time here, I'm subtracting 4 and then squaring it. And once again, divided by n minus 1. All right, I guess I don't need the split anymore. All right, so now it's just a question of solving for it. So I have 9 plus 1 plus 4 plus 9 plus 9. And that is 8. What do you know? It's exactly 8. Yeah, sometimes it works out nicely. Okay, and then, of course, that's not what we're interested in. And the square root of 8 is approximately equal to 2.828. All right, so finally, at long last, we can wrap this up. So remember, the sample standard, the sample covariance was a half. The two standard deviations are 3.808 and 2.828. And finally, after all the dust settles, we end up with 0.0464. Wow. So yes, it's a positive relationship, but it's incredibly weak. This is a positive, an extremely weak positive relationship. That's how we would describe this. In fact, it's so weak that the two variables are almost independent of each other. That's awfully close to zero. But it didn't ask for that. It just wanted to know what is the sample correlation coefficient. Okay. All right. Now, the rest of this stuff is probability theory, which is good because it's less computationally intensive for the most part, but it can be very conceptual. So here's what I'm going to do here. Like I was saying before, I'm concerned about running out of space with this document. I've had this problem with Word before. Not so much, okay, hold on one second. Not so much with some of the other products that Microsoft makes. But Word, in my experience, runs out of memory very quickly. All right, so that one is safe. We don't have to worry about memory now. I've had enough tragedies before where a lot of the work was lost because I ran out of space. So we're not going to let that happen again. And so I'm going to start up a second one for the rest. And I'll just call it part 2. Okay. And so we can start again right here with number 4. Now, this one is a probability theory question. Now, if you notice here, the coin has been flipped 3 times. All right. Now, I think I may have mentioned this while we were doing this chapter. When you flip the coin 3 times, well, think about this. When you flip a coin, every time you flip the coin, the sample space doubles in size. So what you can do to avoid missing any of those elements is write out a little binary tree. Because otherwise it's easy to overlook some of them. So we have HHH, HHT, HHT. So I'm running out of space already. Hold on. Let me fix that. It's easy to run out of space too. That is one of the unfortunate things about this. HHH, HHT, HHT, no, something went wrong there. Let's try that again. I'm going to start it all over again. All right. All right. There we go. All right, so there's 8 of them. Now, when you write out the sample space though, I find that this particular order is not as helpful as it could be. What I tend to do is try to gather together the ones that have certain numbers of heads. Okay, so in other words, we'll start with the 3 heads. Now there's 3 cases here where there's 2 heads. And it'll be easier, in my opinion, when you're calculating these probabilities, if you keep these all together. The actual order doesn't matter, but so in other words, first you have the case with 3 heads, then you have the 3 cases with 2 heads. And now we're looking for the cases with just 1 head. This one, and this one. So I'm going to do HTT. And again, the order of this part doesn't really matter. And then you save the 3 T's for last. Okay. Why am I doing it this way? Because when you try to determine if one set is a subset of another, it might be easier if they're set up this way. Not that you have to do it this way. Okay. But I think it's just easier. It's just, especially like I said, it'll be easier to construct A and B this way. All right. So by the way, let's just go back to this binary diagram again, or binary tree. You've got heads and tails. Now, if you already have a head, this is the new flip. That's what this is supposed to represent. I'm sorry, no, this is the new flip. So in other words, what's happened here is that after getting an H first, the next flip either has to be a head or a tail. So in other words, if you notice in both of these start with an H. And then what I've done is I've added a head in the first case and a tail in the second. Now over here, we started with a T. Both of these have to start with a T. In the first case, we followed with a head, and the second case, we followed with a tail. Once you've got these in place, if you notice, since this was HH, we have to start with the HH in both. Oh, wait a minute. Oh, I did something wrong here. Hold on. Let me fix this. Not that I've got the wrong ones at the end, but I just realized I violated my own rule there. This was supposed to be HHT, because if you notice, then all right, that's better. And then here we should start with HT and then give it an H. And then here we would have had HT followed by a tail. So in other words, those first 2 are the same. It's the second one that's new. And then here, we start with a TH, followed by an H. And then we have TH followed by a T. And then finally with TT, we have 2 tails followed by a head and then followed by a tail. All right, now they're good. Now they're in the order that they should be, but I still had to rearrange them a little bit, or I chose to rearrange them a little bit when I created the sample space. Okay, in other words, what I wanted, and I'm going to write underneath each one how many heads there are. I wanted to keep them all together. And you see they're not together here. All right. But now underneath, I have successfully combined them back again where they belong. Just because, like I said, it'll be easier to compare them to the events that we're calculating. All right, so now we're golden. All right, so finally, now it doesn't actually ask you to do this, but you really, I don't see how you can get these answers right if you haven't formally written out the sample space. It really is important. And so let's look at A now. A represents at least one head. Now watch how easy this is. At least one head means one or more. And so all I have to do, look at that. Look how simple this is. Because I've organized it according to the heads, I don't have to search for them all and risk missing one of them. Oh, it's already set up for me. Look how easy that is. And then let's look at B. B is defined as at least two tails. Now, at least two tails could be interpreted as 0 or 1 heads. But what we could do is, if you want, you could, underneath here, because it means the same thing, rewrite these as 0 tails. One tail, two tails, and three tails. So B would be these two. Because one or less heads, two or more tails are the same thing in this case. So therefore, look how simple this is. All I have to do is grab these. And I'm all set. And what I've done is I've made sure that I don't miss any of them, because that's really the biggest problem, overlooking one of them. That's the biggest challenge. Make sure you get them all. And now the rest is easy, because since a head and a tail are equally likely to turn up, all the elements in the sample space are equally likely. Since there are 8 elements in the sample space, each possible outcome has a probability of 1/8. All right, so we'll keep that in mind when we calculate these following probabilities. All right, they're all equally likely. So one way we can calculate them, for example, A is very simply 7 out of 8. Why? Because there's 7 elements in A out of 8 for the entire sample space. If that wasn't true, we'd have to calculate each probability individually and add them up. Like we'd have to calculate the probability of HHH and HHT and et cetera. But we don't have to worry about that because they're all equally likely. So that makes things nice and simple. And similarly, B is 4/8 or 1/8. Okay, then the rest of these, of course, come from the rules that we've defined. So we can do that. And what's coming up after this is some more probability, a lot of probabilities. So we'll pick this up after the break. Since I'm running late here, let's come back at about, let's say, 11:40, fully refreshed and ready to jump into the rest of these. And then we'll carry on and finish all of these probability theory questions. Okay. All right. So I think we'll stop for a bit. I think we've all reached our exhaustion point with math for the day, or at least for now. So when we get back, hopefully after having something to eat, we'll be ready to roll. All right, so see you all in a bit. All right, here we are again. All right, so we're started this one already. We've set up the definitions of the sample space and A and B. All right, so once that's been done, the rest of it really comes down to following the rules. Now, for example, here, the probability A union B. Now, there's a couple ways you can go about this. You can actually write out the set that contains all those elements if you want to. In fact, here it might be easier to do that. And if you notice, look at the sets. A contains all of the outcomes except for 3 tails. And B does contain the 3 tails. So you know what? That means the union of these two is the entire sample space. So every element in the sample space is accounted for or belongs to either A or B. So that means this union is the sample space. And so the probability is equal to 1, 8 out of 8 or 1. That's probably the quickest way to do it in this case. You could use the addition rule, but we haven't yet calculated the intersection. But if you look at the next one, the intersection between A and B, if you notice here, what we're trying to do is figure out what elements do they have in common. So what we want to do is take a look at them together. And let's go look up here and see what do they have in common. And you can see these 3 elements overlap with these 3. And again, by setting it up the way I set it up, it's easier to find these without missing something, you know, in my opinion. So therefore, the intersection between the two is simply these 3 elements because that's what they have in common. And now we know from the fact that all of these elements are equally likely to show up when we flip the coin. All we have to do to calculate this probability is count how many elements are in the set relative to the sample space. So we can write that as n of A intersect B. That's the notation we used in the slides. N means number of elements. And therefore, you simply have 3 out of 8. And you're done. That's it. Okay, that's probably your best bet in this case. You don't want to start getting involved with the multiplication rule because you don't have enough information right here. And same thing, the addition rule, you could use it, but at that point, we didn't know the intersection. So it's probably easier to simply write out all the elements and count them. Now, later on, you know, you might be able to use more sophisticated techniques, but now here, for example, you can put just the probability, 1 minus the probability of A, which is 7/8 or 1/8. And then here, your quickest step, you're probably better off doing this. You could, if you wanted to, write out the set that contains all the elements in a complement. And that would work. Because here a complement, for example, would be everything that's not an A, which is simply the 3 tails. And therefore, the probability of that happening is just 1 out of 8. So either way, you're going to get the same answer. There's no question about that. Sorry, it's equal to 1 out of 8. So you can choose whatever technique you want, but I think in this case, it was easier to just simply use the rule directly. But just be aware that you can also do it this way. And again, why, why is the complement of A equal to the 3 tails? Because that's the only element that's missing. All right. Now the B would be a little trickier. B complement, and you can see again why this might not be the best way to go. Let's see, what is missing from B? B is anything with 2 tails. So these first 4 are the complement of B. These are all the cases where we have 1 tail or less. Okay. And so you can see it has to be 4/8. Okay. All right. So always, you know, there's almost invariably more than one way of getting to these results. You just pick the one that you want to use, probably the one that's the quickest and easiest. But, you know, there's almost invariably at least 2 ways of doing these problems. Now, here, remember how these work. These are the so-called conditional probabilities, and they are defined in the following way. Now, we earlier calculated the probability of A intersect B just a few minutes ago, and we discovered that it was 3/8. And we earlier determined that the probability B was 4/8, so there's some cancellation going on here. And so this probability is just simply 3/4 or 0.75. And it's that simple. How about this one? Now in the numerator, we still have the joint probability, but the denominator is a little different now. This time it's the probability of A that's in the denominator. So just remember, the information you have, the second one, the one after the line, is going to be in the denominator. So now here, the 3/8, if you recall, A is equal to 7/8. And so here when we reduce this, we get 3/7. Okay. All right, now these last 3 are the conceptual questions. Are A and B mutually exclusive? Now, as always, there's more than one way of explaining this. No. There's really 3 ways we can explain this one. We can say that A intersect B, which means the set that contains all the elements they have in common is not empty. Okay, so in other words, somewhere up here, yeah, here it is. We noted that the intersection is not empty. So since A and B have at least one element in common, they are not mutually exclusive. And you could also say that the probability of A and B, which we've already calculated to be 3/8, since this probability is not equal to 0, A and B are not mutually exclusive. So, you can take your pick. Which one do you want to use as your explanation? But the answer is, of course, no. They have at least one element in common, which implies that the probability of their intersection is not zero. All right, which is what it would be if they were mutually exclusive. Now, the independence one, remember, how does that work? Well, independence requires two things to be true. And they have to both be true. One is not good enough. So now in our example, remember just a few minutes ago, we showed that the probability of A given B is 3/4. But the probability of A is 7/8. So since these two are not equal to each other, I thought I could find quickly the not equal symbol. Not a problem. I'll show you a trick here. If you use Word on a regular basis, you might find this very helpful. Watch this. I'm going to do something very clever. I don't want to spend an hour searching through that symbol box for the unequal sign. There's a special code that is associated with every one of those symbols. It's called Unicode. In this case, it's 2260. So what I do here is I put 2260 and then I type Alt X and watch what happens. Oh no, it didn't work. There it goes. Oh, because I wasn't supposed to put a space there. Okay, so in other words, if you type the 2260 and then don't leave a space, Alt X converts it into the appropriate symbol. Look at that. How cool is that? And now, I mean, it's in the symbol box, but this symbol box is really big. And in my experience, it's not well organized at all. You could spend hours looking for it and still never find it, or you could get crazy lucky. But I usually don't get crazy lucky. So instead, I look it up on the internet. And there you go. So this means that they are not independent. You don't even have to check the second condition. The first one is false. That's it. You're done. Okay, so that's how you prove it. The first condition is false. Therefore, we're done. Now, if the first condition was true, we'd have to test the second one. And if it is also true, then we have two independent events. But that did not happen here. Now, what about what is the last? Oh, complements, yes. Now, complements require two things to be true. Now, this one, remember we saw before, there's a couple of ways of doing this one. Let's do the probabilities. Since we have them, so in order to prove this, the following conditions must be true for A and B to be complements. Okay, and it's got to be both. Now, in our case, you'll recall that the probability of A union B is 1. But the probability of A intersect B is 3/8. Okay, so in this case, the first one is true, but the second one is not. So therefore, we can conclude A and B are not complements because the second condition failed to be true. Okay, so that's how that's done. And now we're ready. Aha, here's another probability theory question. So we've got a card chosen from a deck. The card is replaced, and then a second card is chosen. Now, by the way, already you know that A and B are independent of each other. So let me just make a note of that somewhere. Since the cards are drawn with replacement, as it's called, A and B are independent. End of story. You don't even have to think about it. Okay. So A represents the first card as a king, the second, B is the second card is black. Now, just like before, we're assuming that all the cards are equally likely to be chosen. As long as it's a standard deck, there's nothing funny going on. It's a standard deck. Every card is equally likely to be chosen. So the probability of A is equal to 4 out of 52 because there are 4 kings in the deck. And I did mention it here too, in case your knowledge of cards is a little rusty. The funny thing is, in this day and age, when people are playing card games on the computer instead of with actual cards, it used to be that everybody was intimately familiar with cards. It was one of the most popular games for people to play before we had video games and all the rest. So now, you're starting to find that a lot of people aren't really that familiar with cards. It's possible that there are people walking around who've never actually played with an actual physical deck of cards. So just in case, I'm writing these out, but it's because of the electronics, the video games and all the rest, that possibly people are starting to forget how cards work. So anyway, with B, 26 out of the 52 cards are black. Of course, the other 52 are red. So if you notice, the sample space, by the way, is implicitly equal to the entire deck. It didn't ask us about that. I'll add that to my note here. The sample space is the entire deck, consisting of 52 cards. We don't need to write them all out. We certainly could, but we're not going to. It would just take forever, and there's no need for it. Now, A complement. Now, for this one, we should probably just use the rule. It's so easy. 1 minus the probability of A would be 1 minus 4 over 52, which is 48 over 52. Same thing with B complement. Let's just use the rule. It's so simple. 1 minus 26 over 52, which, you can reduce that to a half if you want to. Now, take a look at this one. This is a tricky question. A and B, what's the probability that both of these are true? Okay, so here's the answer. Since the cards were drawn with a replacement, A and B are independent. Therefore, we can use the simplified multiplication rule for this question. Okay, well, that was a little tricky. Basically, all you're going to do is multiply the probability of A times the probability of B, which we know is 4 over 52. Times 26 over 52. And if you multiply those out, you're getting 104 over 2704. And let's see, what does that work out to be? Oh boy. it reduces very simply, very nicely to 1 out of 26, if you want to. Otherwise, if you want to, you can rewrite it as 0.03. This is fine too. Okay, but it means the same thing. All right, so I'd say that one was kind of borderline tricky, but it wasn't that bad. I don't know if that one is on the test or not, but that was the key to the whole thing. The fact that the cards are drawn with replacement means that the draws are independent of each other, and therefore we can just use the simplified multiplication rule. Now here, this part never changes. A and B, which we just got through showing, is 1 out of 26, is divided by B, which we know is 26 out of 52. Okay. And by the way, algebraically, this is the same thing as 1 over 26. Oh, well, all right, okay. I was going to say, I'm not so sure if this is simplifying anything, but algebraically, I just want to remind you that dividing by a fraction is the same as multiplying by its inverse. So you're going to end up with 52 over 26 squared, 676. Which it turns out to be 1 out of 13. Okay. You don't have to do the reduction. I mean, this is fine. But if you want to, you can convert it to 1/13. Okay. So basically what, all right. So let's do the next one. Now for this one, the only thing that changes is the denominator. This is the one that goes in the bottom. A and B is 1 over 26. A, as you recall from earlier, has a probability of 4 over 52. Algebraically, it's the same thing as, oh, you know what I just noticed here? I could have simplified this like crazy a couple of minutes ago. I was just thinking about it just now. Look at this. Yeah, you see what I could have done? Not that it matters now. We figured it out, but yes, you see, that's what made me think of it. I can do that here too. This one is a half. Okay, well. We missed the opportunity to simplify, but that's okay. We got it. All right, now, are A and B mutually exclusive? No, because, and again, earlier we calculated the probability of A and B, and it turned out not to be 0. We'll just leave it at 1 over 26. Okay, now, Are they independent? Yes. We already know that. Normally, this is not the reason, but I mean, so far, this is the first time we've been able to use this as our justification. Yes, because the cards are drawn with replacement, but we can also show it for another reason. But that's enough. Okay, but if you wanted to go ahead and use the more formal approach, you could say, well, listen, I can prove that the probability of A given B equals the probability of B, and whoops, I wrote the wrong one. Sorry, this is A. So let's do that too, just so you can see that it works out either way. All right, so you'll recall we previously calculated A given B is 1/13. Now, what about A? 4 out of 52. But guess what? 4 out of 52 is just 1/13, isn't it? So this condition holds. And how about this one? B given A, we just showed a minute ago, is 1/2. Is it true that the probability of B is 1/2? Well, let's go find out. We've already done this. Okay, well, there it is. Now, 26 out of 52, of course, is 1/2. That means they both work, and therefore A and B are independent. This proves that A and B are independent. Perfect. But enough, again, it was enough to note that the cards were drawn with replacement. That is enough reason. But if you didn't notice that, this would work just fine. Now, what about complements? Let's see if they're complements. I'm going to say no, but why? Remember, what does it require to be complements? Now, somewhere up here, we calculate the probability of A and B. way back here. Yeah, there it is. And we end up with 1 out of 26, which is not 0, is it? No. That tells us all we need to know. A and B are not complements. Ta-da. All right, well, that one was interesting. Now, here's an interesting question. Look at this one. We just have a bunch of probabilities. We don't know what the sample space is. We don't even know how these numbers were generated. And yet we can still answer all of these questions by using the rules. Oh yeah, look at that. So for example, look how easy a complement is. It's just 0.8. And what about B complement? Now for this one, we're going to use the addition rule because we don't know what's in elements A, sets A and B, but we don't have to know because we can just rely on our old friend, the addition rule. So we have 0.2 plus 0.5 minus 0.2, and we just end up very simply with 0.5. Wow, that was easy. It was a little unusual because of the, what we're used to seeing, but it works. And now how about A given B? All right. We'll use the definition. A and B, as it says on the top, is 0.2 and B is 0.5. Down here, this is, remember, this goes on the bottom. 0.2, A is equal to also 0.2. Wow, so this one is 1. All right. Now we get to do the conceptual questions. Are A and B mutually exclusive? Well, remember, we saw that probability of A intersect B is equal to 0.2, which is not equal to 0. Okay, in other words, it's not 0. How about the independence? Well, let's see. I'm going to say probably not. So we're going to try to show the two conditions. Okay, so we'll start with the first one. A given B, we just showed a minute ago, is 0.4. A is equal to 0.2. So already the answer is no, you can see. So therefore A and B are not independent. Okay, very good. We're done with that one. And now complements, of course. We're looking for two things. We need the probability of their union is the entire sample space, or equal to 1, I should say. And the probability of their intersection is 0. Now, I think, did we do the union? I think we did. We did. The probability of A union B turned out to be 1/2. But that's not equal to 1. So therefore, A and B are not complements. All right, now let's see. 7 is our favorite, our joint probability table. Yeah, and I'm beginning to, I thought this might happen. We're not going to finish this today, and that's fine. There's no real rush because there's still several more to go. I think maybe we'll finish this one up and then we'll stop. And then tomorrow we will pick it up and we'll finish it there. And then I can post the midterm and then you can have a week or so, maybe even a little more to get it done. Okay. So you know what I'll do? I'll post the first half of these solutions today, as soon as we're done. And then this part, I guess we can save it for tomorrow. And no, I'll put this up too, but it's just with the understanding that it's not complete. And then we'll wrap it up tomorrow. So, all right, anyway, let's just get through this and then we'll be done for today. As you can see, there's still quite a few of them left. Oh my God. So we'll be doing this until tomorrow, and that's okay. We have plenty of time, believe me. We're actually, if anything, ahead of where we need to be as far as the schedule goes. We've actually somehow gotten ahead of ourselves, and we're zooming. Let's just put it that way. We're zooming. All right. Let's look at this first one. Now, all the intersection ones you can read right off the table. F and D is the probability of French decaf French roast, right here. R and E is regular espresso. R and G is regular Guatemala. So those are easy. Now, what about F? F is all the French roasts, regardless of whether they're decaf or regular. So that's also quite easy. R is all the regulars, regardless of what flavor they are. With D complement, we can just use the rule. D is right here, 0.5. Now, when it comes to this part, you just have to be aware that the unions are, in this case, unions of columns. So I just want to mention here, note the columns are mutually exclusive of each other, as are the rows. In other words, you can't have the same bean be both French roast and Guatemala. You can't have the same bean being Guatemala and espresso. So what that means is that I can now just simply use the simplified addition rule for the following cases. Okay, so in other words, there's no bean that is both French roast and Guatemala. So I'm literally just adding up the two column totals to come up with 0.68. And if I asked about regular and decaf, it would be the same thing. There's no way that a coffee can be both. So with Guatemala and espresso, I'm literally just, again, adding up the two column totals, and I come up with these. And now finally, these guys we know very well. These are our favorites, I think. Conditional probabilities. Now the DNF is decaf French roast, 0.18. Actually, let me split the screen here so we can see it. Okay, what just happened there? I don't know. All right, here we go. So DNF, like I said, is decaf French roast, which is 0.18. F is that total 0.46. Now, if you want to reduce this, you can. It turns out to be approximately 0.3913. Okay. That's not absolutely necessary. If you wrote it as 0.18 over 0.46, that is fine too. All right. Then the next two will be very similar. R given E will, of course, be written out as in the numerator, we have the probability that both R and E are true divided by the probability of just E. R and E is regular espresso, 0.10 right here. Espresso, the total for espresso is 0.32, and this ratio is about, it's exactly 0.3125. And then finally, we have G given R. Oh, let's see if I can fit that in here. Point 12. The Guatemala, regular Guatemala is 0.12 right here. Regular is 0.50 over here. So that ends up being 0.24. All right. So I'm hoping that up to this point, everything we've done, you were able to do at home. If not, well, there's plenty of time to get ready. You can go back and review, and you can still ask questions about what, if you're not sure about some of these, you can ask questions. And so we'll pick it up. We still have to do the random variables, basically. Normal, binomial, and Poisson are coming next. So we'll do those tomorrow. I'm sure we'll finish those tomorrow. And then we'll start chapter 9, okay, which is like we were talking about the other day. It's all about confidence intervals. So I'll post what we've finished so far, and the rest I'll post tomorrow. And then we'll also have the exam. And I'll name a date, but I'm sure it'll be a minimum of 1 week that you can have to hand it in. All right, because it is kind of long. All right, so I guess we'll stop it here. And then if there's no last minute questions, we can pick it up again tomorrow. All right, how's everyone doing? All right, so assume everything's going well unless you tell me otherwise. So, all right, we'll just start again tomorrow. Same time, same place, and we'll just pick it up with the next batch of questions. Okay, see you then.